Welcome back to ECE 442-542. Homework number 5 is due in April, the first day of April. That's actually pretty soon. The deliverable number 1, if you're in 542 for that project, is due on the same date. There should be a Dropbox for that write-up, which only really consists of a couple, 3 sentences. It's a paragraph. But basically, I want you to be explaining to me what you're doing for your project in 542. As an announcement that's maybe more critical, next week, the next time the lecture is scheduled, we will not be meeting in this classroom. I will not be on campus on Monday of next week, and for that reason, there will not be any office hours on Monday and Tuesday of next week. That's just next week. I haven't canceled office hours for the rest of the semester. It's just for Monday and Tuesday of next week. Our third exam, which we have one more midterm before the final, that is on April 10th so the 10th of next month. Today what I want to do is continue. So relative to me not being around Monday, I will put things on D2L. There might be quite a few things that I actually make available to you. I know you're going to miss the contact time, so I'll give it to you in spades in the video content and the note material maybe. So just keep your eye open for D2L material. Today what I want to do is finish up our shapes. We're back in some lower level grade and we're drawing shapes, circles, hearts, and wedges. But those actually have a connection with their time domain performance spec. Settling time, when you hear settling time, think concentric circles. And as you get smaller and smaller with those circles, what's your settling time doing? And these circles pertain to the distance your two dominant poles are away from the origin, the radius of those circles. As those circles collapse, what happens to your settling time? So, okay, he says settling time, I see circles, but I don't really have a connection with the diameter or the radius of those circles. Well, that's the connection I want you to make. And you could think, okay, if I'm at the unit circle, what's my decay? There is no decay if I'm on the unit circle for those dominant modes. Now if I step inside, make my radius a little bit smaller, then now I start to decay. And as I step further in towards the origin, my decay becomes more rapid. My settling time then in absolute time, which is T settle, or in number of sample periods, reduces as my circles get smaller. These concentric circles then correspond to settling time, with smaller circles meaning faster or shorter in duration settling time. Percent overshoot, you can think of PO, percent overshoot, or zeta, the damping ratio, and that corresponds to hearts, and we'll try to draw those hearts today. I apologize that we're a month late. We should have maybe been doing those not on Pi Day, but on 2/14 of 2019. But those hearts are actually on their side, and they're a little bit distorted. They're actually logarithmic spirals, but who thinks of logarithmic spirals as a geometric shape? Hearts maybe you can see as a geometric shape, and they're on their side. We'll see how those arise today, and the peak time, you could think of those as being an angle that the dominant poles live on, or maybe wedges if we're talking shapes. Maybe an angle isn't a shape. So I said, let's make these all shapes. Now we have a wedge. And if you think of that wedge getting steeper, that's a bigger angle. That will correspond to shorter peak time or a faster rise time or a faster time to peak. That's what the wedge shape corresponds to. We'll try to summarize these performance specifications with a table. And that table, and here, I guess all over this set of notes, you should see a thumbprint. These are all sort of rules of thumb. They're not exact rules, and they go to pieces when you start throwing zeros in on your transfer function. These are just used as guides to help us get an idea, where do I want my dominant poles? Well, here's a first cut at where you might want them based on some of these performance specifications. We'll create a table that indicates how pairs of these performance specifications can be used to create dominant pole locations. And what do we need for a location on that Z-plane dartboard inside the unit circle? If we're now locating poles in that Z-plane inside the unit circle, we really just need to know their real part and imaginary part, or their radius and angle. Getting feedback here. This is a controls class. I now have to stand in a corner. So now I'll talk to you now in the corner with my nose up against the wall, and maybe I won't have feedback. So if I get underneath a speaker, I have problems. So it's not you that I'm making a face about. It's probably what I'm hearing, and I can't hear anyway. So I'm sure you're really wondering, what in the heck? Would he just go in a corner and talk? So here's what we're going to try to do, and this may be next time with some MATLAB step responses, meaning that might be what you look at over the weekend depending on how quickly I get this onto D2L, or maybe that's what you look at Monday when we're not dealing with it in class. Once we have these pole locations, we can now create transfer functions in MATLAB, and we can generate step responses. If you want to now obtain a good insight into these transfer functions' behavior, just start putting these transfer functions into MATLAB and creating step responses. And you can start to see how the zeros impact these responses, how the pole locations, if I vary zeta, if I vary omega sub d, if I vary the wedge, if I vary the heart. And these hearts, you have to use your imagination. Sometimes they're very fat, sometimes they're very thin. And if they have a zeta of 1, that heart is just a line. So again, you have to use your imagination. You're just living on the real line with a zeta equal to 1. And you can put these logarithmic spirals, the hearts, these concentric circles, and these angles on your z-plane plot with this function command in MATLAB z-grid. Draw the z-grid on this pole zero diagram. We'll talk about sampling period and how that's connected to the Nyquist frequency and aliasing. What's going to happen if we do have aliasing, or what is aliasing? What if the performance specifications are incompatible? What if this wedge is not compatible with my circle or with my heart? How do I resolve that incompatibility or that mismatch of constraints? And then we'll start working with controller design, and in fact we'll start with a fairly recent controller design. I think it was in 1950s that it was created, but it's really to give us some insight into what we will do later, and that's the Ragazzini design. And there's already material on D2L describing the Ragazzini design. It may be a interesting read without talking about it first, but you can quickly read it and try to get a feel for that when we start talking about the Ragazzini design. That now makes connections between how do we specify our desired closed-loop transfer function, this t sub c of z, how do we maybe put in zeros? How do we locate our poles? How do we establish the DC gain? How do we build this t sub c of z? And that is dependent on what we're given with our initial system. We'll get there as we talk about the overview of controller design. Let's continue performance specification material from where we left off last time. We have the three specifications. We have settling time spec, we have percent overshoot specification, and then we have peak time specification. Three different time domain specifications. With respect to settling time, I mentioned when we were talking about where we wanted to go today, and I'm really happy that you're here today. Thank you. So you came to class, that's one place that you went, but where we were going was when you see or hear settling time, you're thinking circles, concentric circles. And you could be given that information, settling time information, a couple of different ways. Let's start by saying somebody gives you an absolute time for the settling time that they want to accomplish. What does that correspond to relative to how big is this circle? What's the radial distance of, or radius of this circle in the z-plane? And if you have a t-settle, what do you immediately know has to happen with respect to this r?
Less than 1.
It has to be less than 1. If r is bigger than 1, we're definitely not settling. If r is equal to 1, we're just bouncing back and forth with some oscillation. We're not settling. R needs to be less than 1 if we have a settling time. Once we're given this settling time, now we can describe that either in terms of the absolute time, which is t-settle or t-set, or we could specify it in terms of the number of sample periods. How many sample periods is it going to take before we've gone 1% of our starting value? And that's what I'm showing here. For a single pole, if we now were on the real line, and this radius is effective even if we're off the real line, but it's easy to formulate when it's on the real line, when r is real, but it can now just be a distance away from the origin. That's our radius, r. We keep hitting it with however many samples we've progressed, and if we've now progressed through capital N sub s, how many of those does it take before r raised to the n sub s power becomes 0.01? That's our 1% settling time. That's the definition. Well, that leads then to this relationship. We can cancel out the initial condition. That's the same on both sides. And x at n is r to the n, x of 0, and now we're just replacing little n with a particular number of samples, capital N sub s, which we want that to be less than or equal to 0.01 for a 1% settling time. We're raising this radial value, this radius, to r sub n and saying it needs to be 0.01, but it can be less than that. But that's sort of this bound that we're trying to get equal to or less than. If we take the logarithm base 10, since we have a 0.01 on the right, the log base 10 of that becomes clean. It becomes just -2. And now we can use the properties of the logarithm, r to the n. If we take the log of that, that exponent comes and multiplies the logarithm. Or we now have n sub s log base 10 of r is equal to -2. And we can isolate log base 10, and we're going to give that equation a star. Since we will refer to it several times, when I say go back to star, this is the relationship. It's all based on settling time. If you wanted something to pin on your refrigerator tonight, you can put that star, really the equation. Or you can put it on You probably still haven't run out of index cards. If you should have, that was part of your kit into this class, wasn't it? A stack of, what, 1,000 3x5 index cards? That's probably why I had a stiff neck this last week, is because I was sleeping on a stack of index cards. It's still stiff. I need to spread those cards out, don't I? I'm just making sure you guys are staying awake at 5:30 in the evening. So we can solve for R. And what are we meaning? The thinking behind this expression for R, when we solve for R in that star equation, really n sub s, if we want to get to our 1% settling time fast, that means we want to get there in very few samples. N sub s better be small. If n sub s is small, and knowing what we know about our circles, we would expect our circle to be smaller than if n sub s was big. If n sub s was 100 samples versus n sub s equal to 10, that's going to make a big difference in our radius, or the value of capital R. That's the thinking. When you plug in a particular value for n sub s, you're going to generate an R, and you can plug in a couple different values for n sub s and get this perspective on the radius of these circles. For example, if we said, suppose that we had n sub s equal to 60, and I think I'm still rewinding and fast forwarding through last lecture, aren't I? Didn't we get to this point last time? 60? Do you remember 60? 60. 60. No, you don't remember 60? It was in your calculator. Did you forget your calculator? You didn't think I could see you shaking your head from the back. You thought my nose was still in the wall, buried in the corner. Fooled you. That's okay. We're all friends, I hope, in this class, even though I pick on some of you. But now suppose n sub s is 60. Then we can plug that into our formula, and we see that our radius of our dominant poles needs to be 0.92. So we're not very far into the unit circle. But that's quite a few samples, or it seems like it's 60 samples to get to our 1% settling time. But what that means in terms of absolute settle depends obviously on the sample period. If our sample period is 100 milliseconds, or 0.1 seconds, then t settle would be 6 seconds. It would take us 6 seconds before we would have our 1% settling time. If we're sampling 10 times as fast, if we're sampling at 0.01 seconds or at 10 milliseconds, then it's going to, our system will be settled. Our 1% settling time will occur in 0.6 seconds or in 600 milliseconds. That number of samples then depends obviously on capital T. Sometimes we won't even introduce a capital T, but if we're talking absolute time, we're going to need to know what is our sample period, and what our sample period is influences what our settling time is in absolute seconds. Question?
So you're saying 1 over r to the 1/30th is 60, so that's r equals 0.926?
So now what I'm saying, I hope I did the algebra right. I said r to the minus 2 over 60. So now I'm having a negative exponent. I just said, I don't want to think about negative exponents. I put it downstairs. I now have 1 over r raised to the 2 over 60. I canceled the 2, and I said r raised to the 1 over 30. And a way to maybe think about this is r to the 0 is how big? 1. So now 1 over 30 is a little bigger than 0. So r raised to the something a little bit bigger than 0 should be something a little bit bigger than 1. And how much bigger it is than 1, obviously, when we divide it into 1, gives us 0.926. I'm not sure I answered your question.
Did you already know what R was?
But, oh. So now I get your question. R is, I should have not done it the way I did it. I'm actually solving for R here. R is equal to 10 to the minus 2 over n sub s. So did I do the, wow.
So 10 instead of R.
I told you I was sleeping. Thank you for waking me up. So now R is 0.926. Is that okay?
Because it's 10 to the negative 2 over 60.
So that's because this is now 10 to the minus 2 over 60.
Okay.
And this is now I'm going backwards, but this is 1 over 10 to the 1 over 30. Is that better? Thank you for correcting. I was just making sure you guys were awake, actually. I wanted to see who's going to wake up and question what I've just written down on the screen. Thank you for, following my lead. Is that clear now, if it wasn't before? Now R is 0.926, and that's not too much inside 1, but that now tells us even if our pole is at 0.926, what that corresponds to in absolute settling time depends on capital T, our sample period. So our pole may be stuck at 0.926, but depending on what capital T is, our sample period, that may correspond to 6-second settling time or a 0.6-second settling time, even though our pole is still at 0.926. Is that better? Or a little bit clearer? What if I went the other way? What if I was, you know what, I was writing these notes late last night. That's what the problem was. I apologize. My notes are correct. My writing is wrong. It was wrong. Now I think it's corrected. Okay? Given R, what is n sub s? How many sample periods does it take us to get 1% to where we started? And again, we're using star, which is log base 10. Now I'm going to start questioning every line on this page. But we now have, this is equation star. Log base 10 of R is minus 2 over n sub s. We can now solve that for n sub s. But we have n sub s as an integer. And that's why I'm introducing this ceiling function. I'm not sure if that's really a function, but that's what I'm going to use or create. And simply say that's the smallest integer that's greater than what's inside or underneath that ceiling operation. I want to now plug in an R and see how many samples is that going to correspond to for a 1% settling time. Oh, now I need to start writing. So, suppose R is 0.8. How many samples does that correspond to? Well, now we have the formula right there. It's just a matter of plugging the number into that formula. N sub s, the number of samples to settle to 1% of where we started, is now minus 2 over log base 10 of 0.8. And log base 10 of 0.8, if I did the math right, is minus 0.09691. The the negative signs cancel, which is good. We have a positive value for sample periods, and that underneath the ceiling function is 20.64, which says that if we're really talking about samples, we have to sample at least 21 times before we get to something less than 1% or 0.01 of where we started. Does that example make sense? Make sure I'm not sleeping. Or asleep at the wheel. Isn't that an expression? Yeah. Well, now, if you've taken this class, that's one of the objectives, is you want to be able to fall asleep at the wheel, because you're going to be designing autonomous vehicles, right? Driverless cars. That's one of the objectives of this class, is to be able to figure out how to use this in a control scenario. How do you keep this car going from point A to point B, well, and you can still sleep in the car without somebody else driving either. It's the machine. It's all in the machine. What have we tried to say? We've tried to say that performance specification number 1, which was dealing with settling time, that's now T-settle. If I say T-settle, what do you see? Now, if somebody's walking down the hall and they say, what in the world is he talking about? I see circles. I see circles. We need to cover these windows so they can't see into this classroom. They can hear, but they don't know what we're talking about. But now, if we're dealing with settling time, you should be seeing or thinking circles. Or R. But circles just sounds better than R. I see R. Who's named R? No, let's talk circles. Let's now look at the second performance specification. Percent overshoot. And if we are dealing with percent overshoot, then we're talking about a damping ratio, zeta. And zeta lives between 0 and 1 when we have a percent overshoot. The formula for that relationship between percent overshoot and zeta, if I give you percent overshoot in percent, then you can calculate zeta. It's the natural log of PO over 100 divided by pi squared plus the natural log squared. So you have that twice in your formula, once upstairs and once downstairs. And what you don't want to forget is to take the square root of that. That's the relationship between a second order underdamped system's damping ratio, zeta, and percent overshoot. Or you could draw or generate in MATLAB or in some textbook, you could have this curve that corresponds to percent overshoot versus zeta. With that being said, let's now look at these two complex planes that we need to be comfortable with in this class, making the connection between these two planes. Suppose now, this is the S-plane, now I have let's say that's a quarter of a circle. If I'm living on that quarter of a circle, what parameter does that correspond to? Does that correspond to the damping ratio, zeta? Does that correspond to the natural frequency? Does it correspond to the damping, sigma? Does it correspond to the damped frequency, omega sub d? So now if I'm walking along that circle, what remains constant of those different parameters? Or geometrically, what am I doing on that circle relative to the origin? Is my distance from the origin changing? No. And what doesn't change, distance from the origin wise, relative to zeta, the damping ratio, the natural frequency, the damped frequency, and sigma? This is now the natural frequency. So the distance, or the hypotenuse, the distance away from the origin in the S-plane, corresponds to omega sub n. What if I now sketched an angle in the complex S-plane? Here is now the point omega sub n. If I'm now walking on that angle, what of my parameters is staying constant? The natural frequency, you can discount that one because that was the distance away from the origin. Damping ratio, sigma, damping, or omega sub d, the damped frequency. If I'm walking on that angle, this is now an angle of theta. And now it's clear to me, but it may be confusing to you. I'm going to be talking about two different thetas. Theta, without a subscript, is going to be living in the S-plane. Theta sub d is going to be an angle in the Z-plane. And they are actually defined relative to different real line segments. Theta in the S-plane is defined positive relative to the negative real axis. Theta sub d, which I'm going to subsequently draw in the Z-plane, is going to be the angle in the Z-plane, but it's measured positively relative to the positive real line. So it's clear to me, but it may be confusing to you. That's why I'm trying to make the point now. Don't get confused on the different thetas. Theta is in the S-plane, theta sub d is in the Z-plane. What's constant on that angle, or where that line now has a constant angle of theta? Theta. But if the angle is constant, what parameter does that correspond to? That's the damping ratio. So zeta is fixed on that particular line. So on that line, I can actually be different locations for omega sub n. But once I've drawn that point, that one point, hopefully you can see that I now could talk about a zeta omega sub n, or a sigma, at that particular point. That's the sigma that we've talked about, but that sigma value, the damping, actually changes if we change our distance away from the origin, if we change our natural frequency, omega sub n, even though zeta is fixed. Now what we want to do is talk about what varying points in the S-plane correspond to in the Z-plane. And to do that, let me start developing some formulas. Relative to cosine of theta, we can describe that angle, and now we're really not getting very, what do I want to say, complicated in our geometrical shapes. We're just dealing with a right triangle. if we have an angle of theta and we know that we're omega sub n in the hypotenuse length, then what's the cosine of theta in terms of these parameters that we've identified in our picture? Cosine of theta is, in trigonometric terms, is adjacent over hypotenuse, isn't it? In this case, what's the adjacent length? Isn't that sigma over the hypotenuse, which is omega sub n? That's the cosine of theta, the way we define theta, and omega sub n and sigma. But sigma is also zeta omega sub n over omega sub n, or that's zeta. So if I fix the angle theta, do you see immediately that I fixed the damping ratio? You give me a theta, and I can give you the damping ratio. I can just take the cosine of theta. Or if somebody gives me the damping ratio, you can do the inverse. So you can now say that theta is equal to the inverse cosine of zeta. That's the relationship between damping ratio and theta in the complex S-plane. This is now in the S-plane. That angle theta is the angle in the S-plane. Let's now map that into the Z-plane. There's our bar of soap. Nobody's zestfully clean. So now we have Z is equal to e to the st. There's zest. We just have to put an equal sign. So in your vocabulary quiz, that probably wouldn't get you credit, would it, if you spelled zest as Z equal e to the st. But we're okay. I'll give you full credit for zest spelled that way. All right. Now what is S written in terms of our parameter values? S we can equivalently write as minus zeta omega sub n, that's the real component, plus j omega sub n square root of 1 minus zeta squared. And all of that is multiplied by t. This is just another way to parameterize S, where S is sitting at a point in the complex plane at minus zeta omega sub n plus j omega sub n square root of 1 minus zeta squared. That's the point right here. I didn't really want to circle that, but I did. That's the point S. It has a real part of minus zeta omega sub n, and it has an imaginary part, omega sub d, which is equal to omega sub n square root of 1 minus zeta squared. And you can do the math to find or to derive that relationship. So in rectangular form, there is S. Let's now distribute the t into both pieces and separate that exponent into a product of exponents. This is now e to the minus zeta omega sub n t times e to the j omega sub n t square root of 1 minus zeta squared. And we can now think of that as here is actually our radius, r, in the complex z-plane. We're mapping that point S in the S-plane into the z-plane. And this piece we will write as e to the j theta sub d. So that every point in that exponent, or every variable in that exponent that's multiplying j is really how we're defining theta sub d, and this theta sub d is our angle in the z-plane. Or we can now put that over here and we can say, oh, for a given s value in the s-plane, we are now at a point, let's say right there, which is a distance r and an angle theta sub d. That's our z-plane point consistent with our point S in the S-plane. Now what we want to do is look at what happens for constant damping ratios. What does that look like as far as a curve shape in the z-plane? And so now what we want to do is fix zeta in these two pieces that describe z and vary t. We're going to stay fixed. That's our sample period. We can vary omega sub n. In the s-plane, that really says that if we're keeping zeta, our damping ratio, fixed, now what we're doing is we're walking along this angle, and maybe this point has a natural frequency of omega sub n sub 1. Maybe this is now a value of omega sub n sub 2, etc. And maybe up here is a point omega sub n sub 3, still on that same angle. Everybody comfortable with what I'm doing? Now I'm walking at the same angle in the complex S-plane, and each point that I've labeled corresponds to a different natural frequency, but the zeta, the damping ratio, is the same. What does that look like when we start mapping that in the complex Z-plane? And here's the connection. We fix zeta in capital R and e to the j theta sub d, and we try to get a feel for what does R do and what does theta sub d do. They're both functions of omega sub n, are they not? Now we're going to plug in different values for omega sub n. T is fixed, and the damping ratio zeta is fixed. So let's try to think this through. Suppose we now fix damping ratio, and now we plug in omega sub n sub 1. What is, let's call it R sub 1. When we've plugged in for omega sub n, we've replaced that with omega sub n sub 1. R is just e to the minus zeta omega sub n t. This now becomes e to the minus zeta. That was fixed. Omega sub n sub 1 and t was fixed. Okay, so what? That gives us an R1. Well, let's now compare that to different values of omega sub n sub 2, or omega sub n's. Suppose we look at omega sub n sub 2. R sub 2 is e to the minus zeta omega sub n sub 2 t. And now what we want to do is start comparing R1 to R2 for different values of omega sub n1 and omega sub n2 in the way that I've drawn them. And just to make sure that the progression is consistent, let's now plug in omega sub n sub 3. That says R sub 3 is now e to the minus zeta omega sub n sub 3 t. In moving this direction in the omega, what are we doing with omega sub n sub I? Increasing or decreasing omega sub n? And I'm saying that those values are consistent with this S domain or S-plane plot. So obviously omega sub n1 is less than omega sub n2, or omega sub n2 is bigger than omega sub n1, etc. So this is increasing. Omega sub n sub I. What does that correspond to over here relative to R? What happens to R sub I? Is it increasing or decreasing in those lines from top to bottom? It's getting smaller, isn't it? Because the omegas are getting bigger. We haven't changed zeta and t. We're increasing the exponent, and we have a minus sign in the exponent. So this is now corresponding to decreasing R sub I. That means that in the z-plane, in the s-plane, when we get a bigger and bigger natural frequency, what we're doing in the z-plane is actually collapsing or getting smaller with our circles. We're getting faster in frequency by making R smaller. All right, but it's not just R that's impacted in our z-plane plot or z-plane point when we change omega sub n. It also influences theta sub d, because theta sub d is a function of omega sub n. So let's look at that. Theta sub d sub 1 is now omega sub n sub 1 t square root of 1 minus zeta squared. Theta sub d sub 2, omega sub n sub 2 t square root of 1 minus zeta squared. Theta sub d sub 3 is omega sub n sub 3 t square root of 1 minus zeta squared. What's happening over here to theta as we move from theta d1 to theta d2 to theta sub d sub 3? It's now increasing. Or relative to these values, we have R sub 3 is less than R sub 2 is less than R1 for the appropriate omega, and theta d1 is smaller than theta d2 is smaller than theta d3. So what I want to do is sketch that in the complex z-plane. So what happens, to get us started, what happens when, well, suppose zeta is equal to 0. Where are we in the s-plane when zeta is equal to 0? How much damping do we have when our damping ratio is 0? 100%. Just the opposite, right? If we have 0 damping, what did I ask? Did I ask the wrong question? If zeta is 0, where are we in the complex plane relative to this first omega sub n curve? We're on the imaginary axis, right? We have no damping. All we're doing is shaking. This is the point right here, zeta equal to 0. If we're at zeta equal to 0, and what does that correspond to in terms of a point or points on the z-plane? If we now change omega sub n's, where do we live in the z-plane? If we were doing frequency response, Here's another way of asking the same information. Where did that put us in the z-plane? If we're on the imaginary axis in the s-plane, where are we in the z-plane? On the unit circle. So as we change our natural frequency, we're stepping around the unit circle. As omega sub n gets bigger, we're moving further and further around. We have a limit in the z-plane as far as how high we can go in frequency, but we get bigger frequencies from DC at 1, z equal to 1, all the way over to minus 1. Question?
So when you change omega sub n, walking around the unit circle in the z-plane?
So when we change omega sub n, when we grow omega sub n, I don't know if I like these colors, but let me, and I definitely don't like that label. So that's supposed to be plus 1. As we start at DC, we are right here. And at the highest frequency that we can possibly get in the z-plane, we're at minus 1. And in between those two extremes, we're on the unit circle. So when we're halfway between those, we're at J in the z-plane.
But changing omega sub n doesn't change the position in the s-plane?
Changing omega sub n in the z-plane puts us, and this is supposed to be a unit circle. That's zeta equal to 0. And what does changing omega sub n correspond to in the s-plane? If we're on the imaginary axis, we're just going up, aren't we? So we move up the vertical axis, we get bigger and bigger omega sub n, bigger and bigger natural frequency. How fast are we shaking? If we get higher up, we're shaking faster. Our natural frequency, it's not damped, we just continue to shake. We're shaking faster and faster as we walk up the imaginary axis. We're shaking faster and faster in the z-plane, but we're staying now on the unit circle. Now, suppose that I change that zeta value. Suppose, and what happens when I change the zeta value? When zeta was 0, I was vertical, wasn't I? When zeta is equal to 1, where am I? Then I'm all the way here to like a critical damped position. And now natural frequency is really a real damping amount. The frequency is really sort of the exponential decay speed. Let's go between there. Suppose I now pick a zeta value between 0 and 1. What if I say a zeta value of 0.9? Where am I? Bigger than 45 degrees with that theta, or smaller? Smaller. So now I'm a more acute angle for theta. And what does that look like in the z-plane when zeta is fixed at 0.9? Now I'm at, let's say, a small angle in the s-plane, and I walk along that angle to increase omega sub n, my natural frequency. Well, we just said what happens to r and theta sub d as we fix zeta. Now zeta is fixed at 0.9, and now we vary omega n. Well, we decrease r, so we're collapsing in distance away from the origin, but what happens to our angle? It gets bigger, doesn't it? So can you draw that in the z-plane? We are shrinking in r. We're getting close. Our radius is getting smaller, but our angle is getting bigger. That's what happens. This is fixed zeta. This is, use your imagination. You can now plot this in MATLAB to get this more accurate, but let's just say this is now zeta of 0.9. And if you look at the mirror image of that, all of these are mirrored Do you kind of see the shape that I'm hoping that you see? Now this is supposed to be like that. That's a logarithmic spiral. The radius is decreasing as the angle is increasing. And the angle is measured relative to the positive real line, and the radius is measured as the distance away from the origin. We now have this logarithmic spiral. What if zeta is 0.2? Now we are closer to zeta equal to 0, and this logarithmic spiral, I wish I could draw better than I can, but now it looks like sort of a bigger heart. Do you see why I'm calling them hearts? And the correct answer is yes. Don't give me the wrong answer on that one. But do you see how these logarithmic spirals, and what do those correspond to? Those correspond to fixed zetas, and what do zetas correspond to in the time domain? Percent overshoot. If we have a smaller zeta, if we're getting bigger with our heart, we're getting closer to the unit circle, we have more overshoot in our oscillating step response. And zeta of 0.7, what's that angle look like in the S-plane? A zeta of 0.7. That's 45 degrees for 0.7. So the cosine of 45 is 0.707. 45 degrees. Now zeta of 0.7, that corresponded to a 5% overshoot. And do you see that that's going to be closer to 0.9 than to 0.2? But we'll have a certain size of a heart shape in the z-plane with zeta equal to 0.7. That's what I wanted to say relative to performance specification number 2. Percent overshoot corresponds to these heart shapes in the z-plane, or logarithmic spirals. And if you use your imagination, you can sort of see those as hearts. What do we have for possibilities?
In the S-plane, the zeta is the damping ratio.
So in the S-plane and the Z-plane, the zeta is the damping ratio.
Why wouldn't 45 degrees be 0.5?
So now in the S-plane, 45 degrees, what does that correspond to in terms of zeta value? Is it clear what I'm trying to say? If, well, this isn't connected with possibilities. Maybe I want to add a page. Well, no, needs to be, where are we? Right here. So theta equal to 45 degrees. That now corresponds to what? That has, if we wanted to think of a right triangle, which here's my right triangle, here's a side of 1 and here's a side of 1. And now I have is that true? And now what's the length of this hypotenuse? Pythagorean says it's the square root of 1 squared plus 1 squared, or the square root of 2. And now what's the cosine of 45 degrees? Adjacent over hypotenuse, which is now square root of 2 over 2. And what's the square root of 2? 1.414. Divide that by 2, 0.707. So our zeta of 0.7 is corresponding to an angle of 45 degrees. So a damping ratio of 0.7 gives us this 45-degree angle. Now, let's look at what we can maybe do with that. So here was the zeta equal 0.7 question. Let's now look at a possibility relative to what we've already introduced. We've introduced two different performance specifications. Suppose we combine those. Combining design specs. Suppose we have a possibility. We have T-settle and percent overshoot specified. If we now have specified a settling time, what do you see? Humor me. Circles, right? So you have settling time. This now leads to R. There's circles. What about percent overshoot? That gives rise to zeta, and if I have fixed zetas in the z-plane, it's no longer angles like they are in the s-plane. They're now logarithmic spirals, or you're now seeing hearts. If somebody gives you a percent overshoot, now you're seeing hearts. And I don't know why I didn't switch to red. I apologize. But you now have red for hearts. So what we have is something like this. We have settling time is giving us this, and percent overshoot is giving us this. And we want to know, where do those intersect? We have circles and hearts, and we want to know, can we find the intersection of those lines? We give a fixed zeta, and we get a fixed R. Those are two lines they're going to intersect, and we want to know, where do they intersect? That's our pole location. Where are the pole locations? So we're given R and zeta based on settling time and percent overshoot. We want to now find where those intersect, or what is R e to the j theta sub d. We want to know if they intersect, they define some point in the z-plane, and if we're at a point in the z-plane, we can draw that in the z-plane, and we can find its distance from the origin and the angle it makes with the real axis. We can find R and theta sub d. So if you were good at sketching, which you know I'm not, you could find that with a sketch by drawing the correct circle and the correct logarithmic spiral. We're given R once we have T settle. We aren't given theta sub d directly. So now let's find analytically the connection. R is now e to the minus zeta omega sub n t. This is sigma. So you could see that as e to the minus sigma t. If we take the natural log of both sides, we can say, oh, the natural log of capital R, our radius, is now equal to minus zeta omega sub n t. Or we can now solve that for omega sub n t. Now you kind of have to just believe, what the world is he doing? Well, it'll make sense in a minute. We can now solve this for this product, natural frequency times the sample period, and that now gives us natural log of R over minus zeta. or we can just put that minus in front of both, or the ratio or the quotient of natural log of r over zeta. Therefore, what was theta sub d? Theta sub d was omega sub d t, the damped frequency times the sample period. But we know what the damped frequency is in terms of natural frequency and zeta. That's omega sub n square root of 1 minus zeta squared. That was the real component of our, that was the imaginary component of our location in the S-plane times t. Well, that t can be slid around. It's just a scalar. Let's now slide it in and have it be the product, omega sub n t times the square root of 1 minus zeta squared. We now know what omega sub n t is from above in blue. And now we've eliminated the natural frequency and the sample period, and we have an angle description in terms of r and zeta. R we have from settling time, zeta from percent overshoot. Now, once somebody gives you those two specifications, you can say, oh, theta sub d is actually minus natural log of r over zeta, that's omega sub n t, times the square root of 1 minus zeta squared. And we now have our location analytically in the complex z-plane. Z sub d, we have r, that was given by, when do we see circles? What performance spec gives us circles? Settling time. So settling time gave us immediately, directly r. Then we have e to the j theta sub d, and theta sub d we've derived theta sub d from, or in terms of, r and zeta. So you give me those two specs, I can now find you a location in the complex z-plane analytically in terms of r and zeta. One more. We can talk now about the third performance specification, which is the time to peak. Or maybe I'll just refer to it as the peak time. For a second order underdamped system in the analog or continuous time setting, the peak time is where we first peak after time t equals 0, and that's equal to pi over omega sub d. That we can derive. And we can solve that for omega sub d, which is now pi over time to peak. And you're getting good at this. S is minus sigma plus j omega sub d, which is equal to minus zeta omega sub n plus j omega sub n square root of 1 minus zeta squared. In the S-plane, what does a constant damped frequency look like shape-wise? If I fix omega sub d, where am I walking? That's now horizontal lines, isn't it? That's a particular distance or value of our imaginary component in this complex value S. You specify on omega sub d, you now are determining some horizontal line. Let's say this is now j omega sub d sub 2, and this is j omega sub d sub 1. What does that correspond to in the z-plane? We're now going z is equal to e to the st. S is minus sigma. So that's our r. We now have e to the minus sigma t times e to the j omega d1 t. And in the other case, we have e to the minus sigma t times e to the j omega sub d2 t. Can you now tell me the difference between the blue and the red? Go Wildcats. No, I'm sorry, red and blue. What does that correspond to? If this is a point, if blue is a point in the z-plane, and we fixed omega sub d sub 1 and varied sigma, that's what's happening in the s-plane when we move along that horizontal line at a horizontal height, a vertical height of j omega sub d1. We're just changing sigma. What happens in the z-plane with the blue if we just change sigma? I factored it now as a radius times e to the j theta sub d. Theta sub d for a fixed omega sub d sub 1 is fixed, isn't it? Our angle is fixed. We change sigma. We're just moving r. We're now on an angle or a wedge in the z-plane. And how big is that wedge for omega sub d1 and omega sub d2? Which one is bigger? Which wedge is bigger? Is omega d1 bigger than omega d2 in the s-plane? Which one's further away from the real line? That's pretty simple, isn't it? Omega d2 is bigger. What happens to the angle between theta d1 and theta d2? I'm really not getting impatient. I'm just running out of time. Is it clear what we now have? We now have wedges in the z-plane corresponding to peak time. Which peak time is smaller? The peak time associated with omega d1 or omega d2? Time to peak is pi over omega d. Which of these curves, blue or red, gives us a faster or smaller peak time? Faster and smaller are the same. That's the red. So now if we want a faster peak time, we want a bigger wedge in the z-plane. The wedge is bigger to get a faster peak time. Suppose, as an example, we say a time to peak is 6 sample periods. i.e., time to peak is maybe 6 capital T. Find the wedge. Now what's the wedge? That's what we're doing when we're talking time to peak. The wedge is really what is theta sub d. And theta sub d is omega sub dt. But what is omega sub d? That's t over time to peak. What? Omega sub d is pi over time to peak. I don't know what I just said. But that's now times t. And what was time to peak? We said 6 sample periods. So what is theta sub d for a peak time of 6 sample periods? Theta sub d in radians is pi over 6. In degrees, it's now 30 degrees. So now we have 30 degrees per sample. And I'm out of time. I have plenty more to material. I may put that in after the fact, but now at each sample we're stepping around the z-plane 30 degrees. Do you see how many thetas it's going to take to get us all the way around in one cycle? So now we're just splitting that 360 into wedges of size 30. So it's going to take us, is that 12 samples to get all the way around. And we can now relate this theta sub d to the number of samples in a cycle of a oscillation. With 30 degrees, we now have 12 samples in one cycle of our oscillation. I'll try to fill that in. We also have a whole nother worksheet of performance specification summary, and I think you can see what we're doing there. And we end up with this table. I want you to understand this way of using this table. For given a settling time, percent overshoot, there are your formulas for finding the point z delta. Or you're given settling time and peak time, that immediately gives you z delta, because that gives you a theta and an r. You get a percent overshoot and a peak time. Now you have to solve for r, but you are given theta sub d. That's the combinations of these, and we have to worry about those to find z sub delta. We'll pick up somewhere close to there in a week, but in between time you're going to get some additional material.